Okay, I still have a problem. Anyway, so today we'll go through some standard power reduction techniques in digital CMOS. And this is the reference I'll be using. This is excuse me, book by bunch of people from, I think, Synopsys and ARM. The book is titled Low Power Methodology Manual for System on Chip. It's by Springer, and this is a book which is available online, but and it's you have to buy it. But if you're a Synopsys customer, you get it free. So since our institute is a customer of Synopsys, so we have the online version. I will share that with you later. So you can go through the various chapters of the book for this course. So dynamic power dissipation in CMOS. So this is the power consumed when the CMOS gate is actually switching, right? So here we have one inverter where the input is going from 1 to 0, and then the output charges from 0 to 1. The way the output charges is by charging this capacitor, and it draws current from the power supply. So what is the charge finally stored in the capacitor? If the total capacitance in the output is CL, the load capacitance, and it charges to a voltage V, the charge is CL times V. And since the charge is drawn from the battery which has a voltage V, the energy is voltage times charge. So that is CL V square. And the power is the number of times you do it, or the rate of doing it. And since you do it every t seconds, t is the cycle time of the clock period, so F is 1 by t. So CL V square F is the power. And then half CL V square, because the energy which is drawn from the battery is CL V square, but only half the energy is lost as heat. The remaining half gets stored in the capacitance, right? That is during charging of the capacitance. So that means half CL V square is lost as heat during charging. During discharging, you don't draw any power from the battery, so whatever energy is stored in the capacitor gets lost. So half CL V square again is lost. So whether you are charging or discharging, the power which is lost, which is the power dissipation, is basically half CL V square times F. Now there is an additional factor alpha here. Okay, so we'll just see what alpha is. Alpha is basically, it captures the switching activity, because not every time the node or the net might switch. Okay, so the alpha captures the number of times, the average number of logic transitions in a given cycle. Okay, now this number is usually between 0 and 1. It can be actually sometimes more than 1 also. What does it mean being more than 1? But before doing that, let us just have a look at the typical values for alpha. If you take the signal which is a clock, a net which is a clock, for example, it could be the output of a clock buffer. So every cycle there are two transitions, a rising and a falling, right? That's what a clock waveform is. So for clock net, the alpha is 2. So power dissipation for the clock net, or the gate which drives the clock net, is CV square F, where C is the capacitance of that clock net, because alpha times 0.5 is 1. A typical logic net, alpha is actually much less than 1. So this is here, for example, in this example, for this particular cycle there is exactly one transition. Okay, but if you took, say, 100 cycles, in 100 cycles, if there were, like, say, 5 transitions in 100 cycles, then alpha will be 5 by 100, 0.05. So there is a little, it's kind of probably, you might get confused with this notation. I should probably fix this. Here I just wanted to say that in this cycle the number of transitions is 1. but the way you calculate alpha is you kind of count the number of transitions over a prolonged period and then you average it out. Now you can also see from here that you could have the number of transitions bigger than 2 for a clock has 2, but you can have a logic net which has more than 2 transitions in a clock. There's nothing really preventing it. Okay, and the question is it desirable? No, I mean it's not desirable, but you could have it because you could have a logic net which is somehow chattering up and down due to certain problems in the way the circuit is designed. So it could be jittering. Not jitter is not the right word, but essentially you could have bounce. And in those situations, alpha could be definitely more than what it is supposed to be because there are extra spurious transitions which are happening. These usually happen due to the signals coming into the gate. So there is a logic gate which is driving the net, and we are looking at the number of transitions in the net. If the inputs are coming into that logic gate with different delays, right? So in a clock cycle, it might happen that the input pattern is such that output goes 1, then the input pattern changes because things are still stabilizing. It could go down to 0, then it could become 1 and 0 and so on. So these are what are called hazards, dynamic hazards or glitches. Right? So that is not desirable, and eventually it will settle down to some value which you want to capture. So functionally the circuit might be okay, but from a power perspective it is bad because you are just doing unnecessary switching. So causing you to go alpha up. The question is there a constant alpha value for a particular system? Now the thing is that alpha actually depends on the kind of computation you are doing, right? So for example, if say you have a bus, and if you look in the bus, if the bit patterns, right, always, for example, when you have all ones and it changes to all zeros, you have every bit in the bus is switching, right? Whereas you could have some other bit patterns where maybe just a few bits in the LSB are switching. So the alpha is really a very data dependent number, right? So some data patterns, the same activity, the same computation, but different data patterns could lead to different alpha values. And as I said again, alpha is an average number. It's like it captures the average number of transitions in a clock cycle. Sometimes people call the probability of transition, but as you saw that alpha value could be more than 1 also if there are a lot of glitches. So in that sense, probability is not the most accurate number, the accurate term to use it, right? But most of the time alpha is less than 1, and in fact lot of the data paths, lot of the nets, alpha value is actually less than 10%, perhaps even less than 1%. So so that is kind of what the typical alpha numbers are.
Can you say that the path is actually proportional to?
Yes, absolutely. You see the equation out here, the dynamic power is proportional to the switching activity. More switching activity, more is the power in a linear fashion.
The system to be stable at a point, or we can have spurious activities.
So the question is there, what is the connection between stable system? Probably you're kind of, by using the word stable, you're kind of referring to correct operation, perhaps a stable value of the signal. Now the thing is that if you see in a synchronous design, you have a clock which captures the state of the system every cycle in some sense, right? Because you have all the flops are getting triggered by the clock edge. So the inputs of the flop have to be stable for a duration of at least a setup time. If that is guaranteed, then the system will work properly. What happens before the setup time? Are there a lot of transitions? All that doesn't matter as far as the functional correctness of the system goes. You just have to ensure that final value of the logic net stabilizes at least a setup time before it gets captured by the clock, if that net is connected to the clock. But of course it's not desirable to have a lot of these transitions because you are just unnecessarily wasting power, right? So it's not a So this is basically dynamic power dissipation, right? Now if you look at the capacitance of the net, so we have this logic gate, which in that example I showed as an inverter, but it can be any logic gate. It drives some capacitance which consists of its own capacitance, parasitic capacitance, right? There are source drain junctions, some internal source drain junction capacitance inside the logic gate, the Miller capacitance, etc. Right? And then there is the wiring, because you have a wire which takes the net consists of a wire which connects the output of this gate to the inputs of other logic gates to which this feeds into. So the wire has a capacitance, right? So the wire will have capacitance to the layers below it, layers above it, etc. And then the input of every logic gate this connects to will have its own capacitance, which is basically the gate capacitance of the transistors. You have to sum up all the gate capacitance of all the transistors to which this net is connected to, of all the gates. So that is the gate capacitance. So yes.
This case can load be different from CG.
Pardon?
I have to differentiate between load and CG.
Correct. That is exactly what I am saying, because if you the question is why is C load different from CG, right? So C load consists of three different components. It consists of its own capacitance Cp, and I have indicated the number a scale factor S out here, because when I have a logic gate, we might have a logic gate with a certain size, but in the actual circuit we might want to use a larger size or a smaller size. So suppose we choose the smaller size gate as a unit size gate. For that, let's say the capacitance is Cp. Then any other version of the gate when we instantiate in the circuit will be some scaled version. We might scale it or we might not scale it. Why would you scale it? Why would you size it up? For speed reasons. If you recall from the last semester's lectures on delay minimization, if you want to improve speed, you want to upsize the gates. So you might upsize this gate. And then you have the wire capacitance, because the net is, see here we are talking of the capacitance of the net, which is the output of the gate. So that consists of the self capacitance which is connected to the net, then the parasitic wire, the wire capacitance, and then the gate capacitance of all the gates it's connected to. Here there could be n gates. Usually you don't want n to be too large, right? Maybe 4, 5, 6. Remember we said fan out 4 sizing. So we don't want too much of a spread. The net shouldn't be connecting to too many other gates, but if it's connected to n gates, then CGK is the gate capacitance, the input capacitance of the kth gate, and that kth gate is scaled by a factor Sk. Okay. And so the input capacitance of a gate is linearly related to the size of the gate. If I double the size of the gate capacitance doubles. So you have to sum up all those gate capacitances. So this becomes the total capacitance of the net, and so that essentially gives me the load, the capacitance value which I am switching here, and then of course the supply voltage and the frequency. Now whenever I am switching a gate, besides the power to charge and discharge the capacitance which is there at the output of the gate, what happens is that when I am switching, what are we doing? The input is transitioning from one logic state to another. For example, it could go from logic 0 to logic 1, where the voltage is going from 0 to 1, right? 0 to VDD. When that is happening, for the duration in the middle, both the NMOS stack and the PMOS stack will be on for a short duration. When my input levels are quite static at either logic high or logic low, only one of the pull down or pull up stack is on, the other is supposed to be off. But during the transition, both will be on for a short duration of time. That duration of time is given by how fast or how slow the input transition happens. So during that transition, basically what happens is, for example, if I am going from 0 to 1 at the input, the output is discharging, right? But when the output is discharging, I could also have because I'm turning off the PMOS. Initially it is on, it's turning off, but for a short duration both PMOS and NMOS are on, so I'll have some leakage current. This current, the term to use out here is not leakage but short circuit current, because I'm shorting the VDD and ground. I'm shorting the power and ground out here, so there will be some short circuit current. And if actually if you see that current is a function of time, what will happen is that the current between VDD and ground will be very small, but during the transition, when an edge happens, there will be a spike in the current and then it will go down. It will be almost like a shape of a triangle. You can approximate it well with a triangle, right? Now the thing is that the slower the ramp rate, the slew rate, the more is the duration when I am short circuiting the thing, right? So if I say the short circuit current ISC is the average short circuit current, then the power due to short circuit is V times ISC. Now how do we measure this short circuit current? So it's kind of you cannot measure it in simulation, but in simulation itself, how do you measure it, right? So for example, when you are let us say let's take this case, when the input is going from 0 to 1, the output is going from 1 to 0. So I am discharging this. So the current from the capacitor, the dynamic current, is essentially going through the NMOS from the capacitor. So ideally there should be no current from the PMOS or through the PMOS, because I am just discharging the capacitor. So whatever current comes from the PMOS, you can say is the short circuit current. So you can kind of measure the current. So there are various ways you can measure the total current drawn from the power supply. There are multiple different ways you can try to get to this number. Now the thing is that it's kind of a little tricky to get this number very accurately, because you have all this Miller capacitances, etc. It's a little bit of a tricky thing to get exactly the right number, but it turns out that number is actually pretty small. The short circuit current for a well designed circuit where you have good slew rates, where you have sized things properly, the short circuit power is actually quite it's a small fraction of the overall dynamic power. Usually it's less than 10%. So what we normally do is we kind of ignore the short circuit power, in the sense that short circuit power you reduce by making sure you have good sizing and good ramp rates which are not too slow, and you have small sizes. Right? If I make a gate which is bigger, of course I'll have more short circuit current. But remember that this short circuit current is a current associated with dynamic power, because this happens only when the gate is switching. So the total dynamic power is the power to charge discharge the capacitance plus the short circuit power. So that was the power dissipation due to dynamic activity. Yes.
ISC current is going like zero line
Here. Yes.
then we can't finite value at the time when we are not switching, right?
Okay, so firstly, this is just a cartoon sketch. It is not from actual simulation. In fact, I took this particular picture from some other slide, but it's just a hand-drawn, cartoon sketch. But essentially, it is saying that the intent of the sketch is to convey that as you slow down the edge ramp late, you'll have more and more short circuit current. That is the only message conveyed out here. But when I'm not switching out here on this side, right, and on this side, I have basically what is called leakage current. Right? It's not short circuit current; it's leakage current, and the leakage current happens due to a number of reasons. One is basically the leakage in the diodes. You have parasitic diodes in the source drain junction regions, right? So of course here, if you take this PMOS out here, PMOS consists of a P2N diode out here in both these regions, right? And you have a diode between, in this point out here to the body, which is a PN diode, which is reverse biased. Yeah.
Slide, why should the current magnitude increase with slowing ramp rate? The ramp
So the question is, why is the
This duration should increase, that's okay. But
right, right. See the thing is that what is being shown out here is the total current, which is I don't know how. Okay, so if you measure the total current, okay, then if the output ramp is becoming faster and faster, your capacitance is also lower and lower. So the total current will be lower for faster ramps, right?
yeah, but if this lower means width is lower, that means the resistance should be higher.
No, no, no. We are talking of, we are not changing the size of this gate. The gate is fixed, but the output load capacitance is say reduced. So you have an input of a certain ramp, right? The output load you are reducing, so that you see the changes in the no. So actually here what is happening is that the input ramp is basically being is actually being made faster and faster. So sorry. Right. Right. So this doesn't seem to be a accurate description actually, because if I don't change the output capacitance, then if I'm just changing the input ramp rate, then basically what we'll have is the total right. So right. So this, let's investigate this later, right? So because you would expect the currents, the peak current not to change, but the triangle should become narrow and narrow.
So,
Yeah.
maybe because the capacitance will take some current because as the input is increasing, the output will start increasing. So, there will be some current through the
Huh.
capacitor tube.
That's right. There will be the
So,
even if when you take
some
that into
current will
account.
flow through the NMOS and some current will flow through the capacitance. So, due to that, the
Correct. If you let us say what is being plotted is the total current drawn from the power supply, right?
so even if
So
the input ramp is increasing, the voltage at the output that will also start decreasing at a faster rate. So, the current through the capacitance will be more.
It's a short circuit. So the consist of it goes in both of them. Not
right. So here the if you are looking at the power drawn from the battery out here, then as I am when I am discharging the output capacitance, basically the current from the battery is just there to supply the short circuit current, because the current from the capacitor is just going directly through the NMOS, right? So if you are measuring, if you are looking at that current, then the question is, will the peak of the current change as I am changing the ramp rate, right? So so let us take one extreme where you have a step, ideal step at the input. When you have an ideal step at the input, then what happens is that you should have zero short circuit current from the output, right? So this, in fact, whereas if you have a very slow ramp, then so from that you actually see that so maybe that explains it, that if I have an ideal step, then there is no time for the output even to have changed, and I have actually very little short circuit current out here. So because the short circuit current is kind of determined by the current through the PMOS out here, which is dependent on the the gate to source and the drain to source voltage. So if my gate to source changes very fast and the drain to source has not fallen down yet,
So, but
I mean,
you are saying ideal ramp step input, then why not consider ideal ramp output? You're taking ideal.
no, this is just to see, okay, the, what is it that we are trying to understand out here? We are trying to understand what happens to the shape of this short circuit current and the peak value of the short circuit current, right? No, but we just saw why it could become, in fact, you could have no short circuit current when you have an ideal ramp, right? When you have an ideal step, for example, not ideal ramp, you have an ideal step, then what happens is that, so when you have this step, you have current which is coming, the capacitor current is just falling through the NMOS, but the supply is supplying current through the PMOS, right? So it's the PMOS which essentially is determining the short circuit current. Now if my input step happens very fast, then there is not much time for the output to have reduced, and I think that's what your friend was saying out here, so that I don't have much current anyway from the PMOS. Before the output can react and come down, the PMOS gate is shut off. So I don't have much short circuit current. So actually this is a correct representation of what is happening. The peak currents will also be a function of the peak current of the short circuit current will also, peak value will also be a function of the input ramp. In general, actually it's a lot of times it helps to look at the extreme conditions to get a sense for what is happening. Then you can understand what is happening in between. So here we are saying the extreme is when you have an ideal step, and then you see what happens, and then you say, okay, in the ideal step there is actually no peak is 0, and so it has to kind of go in that time.
So it means that the short circuit current is dependent on the load. The load
Short circuit current also depends on the load, absolutely. So it's a function of both the input ramp rate as well as the output ramp rate, and the output ramp rate depends on the load. Good questions, actually. So the leakage power is the power when I'm not transitioning, but I still draw, my transistors are not fully off, right? So let us say here my input is input is low. So and then I have my NMOS, PMOS is on, but NMOS is supposed to be off. But I have a subthreshold leakage current, because across the NMOS I have a VDS which is not 0, right? So I will have a subthreshold leakage current which is given by IS. Now in addition, actually in this, because this, I could also have leakage out here across the gate of the PMOS even though the arrow is shown out here, but it depends on logic state where I have leakage through the gate. Gate is supposed to be an ideal capacitor, but the gate oxide is very thin, so I will have some tunneling current through the gate oxide. So I will have some gate leakage capacitance, as well as the diodes out here, they will also leak. The diodes are reverse biased, but you will have some leakage current through the reverse biased junctions. So the power due to leakage is essentially voltage times this leakage currents, IS plus IG plus ID. Now typically it's a sub-threshold leakage which dominates, okay, the leakage currents, and you kind of want to make sure your gate leakage, junction leakages are small by using various process recipes, process tricks, because if I have leaky capacitors, there is only so much you can, there's not, it's kind of not a good situation to be in for a circuit designer, okay, if you have leaky capacitors. So that's why the processes try to use higher gate oxide, but then also higher dielectric, etc., to get you the same effect as having a very thin gate oxide, which is required for scaling of transistors. So basically the leakage is largely dominated by the sub-threshold leakage, which, if you recall from the previous class, depends on the supply voltage, the threshold voltage of the transistor Vt, S is the size. Yeah, this is a confusing notation. S is also used for subthreshold slope. Here I wanted to in this particular slide I am using S to represent the size of the gate. Bigger the size, bigger is the current, and temperature, right? It also depends on the temperature. So then if you see what is the total power dissipation, it's the dynamic plus leakage power. And so that is half alpha CL V square F plus V times the leakage current. And if you want to reduce power, you look at all these terms and see how to reduce each of them. Okay, so you cannot reduce half, but you can reduce alpha. Okay, you can reduce the switching capacitance, power supply, the frequency of operation, again power supply, and the leakage currents, right? So these are all the different terms which you have to see how to reduce by various techniques, circuit techniques, architectural techniques, and then of course process related techniques and so on. But one thing you will find is that there is no free lunch. If you try to, especially with techniques related to circuits, circuit related techniques, when you try to reduce power somehow by playing some tricks, you will lose out inevitably in performance. So what that means is that you are actually playing the trade-off game, power versus performance. You have to kind of smartly trade off one versus the other to reduce power dissipation. So we'll just look at a few examples in this class, and then we'll come back and look at more examples in the subsequent classes. So one important net in the chip is the clock net. The clock net connects to all the flops, and modern designs, they are very deeply pipelined. So there are a lot of flops because you want performance. So there are a lot of flops, and each flop, the gate input of the flop, the clock input of the flop presents a capacitance to the clock net, and you could easily have like 500,000 or 1,000,000 flops in your chip, and then these flops are spread out all across the chip uniformly. So pretty much the clock net has to feed and connect to all across. It goes all across the chip. So there's a lot of wiring capacitance also associated with the clock net. So the clock power in synchronous design is kind of the dominant dynamic power. And also the other thing is, if you see the clock net, the switching factor, activity factor is the highest typically, right? It's basically two. There are two transitions per cycle. And so a lot of effort, a lot of attention has gone in to look at how to reduce the clock power. So one technique which is used is what is called clock gating. Many times you will actually you will have a piece of logic which looks like this. That is, you actually sample the inputs only if an enable is there. Okay. Otherwise, I don't look at the input. We are doing some computation. It's a multi-cycle computation only, and some particular cycle I want to look at the output. Otherwise, I don't want to look. I don't want to sample the output. And that is in Verilog code. How do you write it? You have always at pause edge clock, if enable, assign D to Q. Okay, and that can be implemented like this, where you have a bunch of flops. Okay, D is a bus, and then you have muxes in front of it. And if enable is low, what you do is you recirculate the old value. So every clock edge, I am sampling I'm sampling the input to the output, but the input is having the same value as the output when the enable is low. So only when enable is high, I pass in the new D value which gets sampled. But you see, this is not a very efficient way of from a power perspective, because what happens is that your clock net is unnecessarily switching here. It's toggling the clock input of all the flops, even though I didn't need to. And so that is dealt with. The other way of implementing this is what is called clock gating, where you don't you gate the clock. So this G clock input changes only when enable is high. Otherwise it doesn't change. So when it doesn't change, Q retains the old value. Q changes to the new value only when enable is high, right? So this is basically what is clock gating. Now, one thing which, important thing whenever you muck around with the clock is that you want to ensure that you don't create glitches in the clock network. If you go and modify the clock network, you should not create glitches, because every edge in the clock input is very important. The system reacts to an edge because an edge is such an important thing. So you should not create spurious edges through glitches. Right? Then your whole machine will basically go for a toss. And so here you see what we are doing. We are putting an AND gate in series with the clock path. So we have to be careful in how we control the other input of the AND gate. So we don't want when the clock is high, we don't want the other input of the AND gate to go up and down and so on, right? Because then that means the output of the AND gate will also go up and down, and then we have too many edges which can mess up the system. So that input of the clock gate is then the enable input is essentially latched out here, such that, and you see it's a negative edge of the flop of the clock is used to latch the enable input. When I use a negative edge, that means the change of the output of this happens only during the negative edge, just immediately after the negative edge. After that, it remains stable. That is the property of a negative edge triggered flop, right? So it remains stable till the next negative edge. So and then it will change only after the next negative edge has happened. So that means I am assured that during the time the clock is high, this other input of the AND gate is stable, and so I won't have glitches. So just a simple guarding circuit. So your clock gating circuit will be something like this. Typically, what is done is, when you will have buses, 16-bit, 32-bit, etc. buses. So all the flops in the bus, are the clocks are connected, and there will be one clock gating circuit, which is there in the clock path, which gates the clock and then connects to all these other guys. So what is interesting is that you find that actually clock gating helps to reduce area also for this kind of structure, because in a non-clock gated structure, I have so many muxes. Every input, there are 32 muxes out here if it's a 32-bit bus, whereas here there is a single clock gate and there are no, I am removing those 32 muxes. So it actually also helps to reduce the area of the structure. Of course, what you have to keep in mind is that when you introduce this kind of circuitry in the clock path, because now the clock signal has to travel through an extra AND gate out here, right? Now imagine there is another flop somewhere which is creating the data which eventually comes to this, the previous flop in that pipe stage. So now you have to worry about the timing closure property, because you have introduced the skew in the gated clock. The gated clock has a skew compared to a non-gated clock. So you have to account for that explicitly. It's not hard to account. You just have to make sure that everywhere you probably insert this kind of gate, so that all the clocks get delayed by the same amount. So it's not such a difficult problem, but it's just something which has to be paid attention to. There are certain other simple optimizations which people do now. These are all kind of routine things. What I'm saying out here is now well understood, and it's all done now routinely in digital designs. And these are actually these are incorporated as part of the tools. The tools which do the synthesis and power optimization, they will do all of this for you. Okay. So another kind of simple optimization is, say you have a logic circuit like this. You have an AND gate followed by an OR gate. And if it turns out that this particular net is a high activity net, then instead of using these two different gates in your standard cell library, you use a compound gate. In a compound gate, the same gate is incorporating inside it through appropriate creation of the stacks, the AND gate functionality. So when you do that, then there is no explicit wire which is going from one gate to other, and you are reducing the capacitance and hence the power dissipation. So this is why you also have in a standard cell library a lot of gates. You can always make any Boolean function using just an AND gate, right? NAND gate is good enough, right? And an inverter, and you are done. That is a universal gate. In fact, you don't even need an inverter; just an AND gate is good enough. But it doesn't lead to very efficient designs. So you need to have these kinds of compound gates which help you to reduce area, reduce power, etc. And so you need to have a bouquet of such gates, and so that the tool which is synthesizing this can choose the most optimal gate to reduce power and also reduce delay. You also have, sometimes the gates might not be symmetric with respect to the capacitance at the inputs out here. So this is just some gate with multiple inputs, for example, a 4-input NAND gate, and the sizing in this gate is such that the top input has a higher gate capacitance, and if that net is a high activity net, you can just switch it. See, again, it's a very simple common sense type approach. So you are getting the same functionality, but that input is going to that net is being connected to an input pin which has lower capacitance. So again, this is an example of a local transformation in the circuit structure which preserves the functionality but gives you lower power. So something like this, actually, you can say, is not really impacting speed also. So this is probably an example where speed doesn't get impacted, but you're still getting some benefit in power reduction. But these kind of give you small amounts of power reduction, not like big large numbers. Gate sizing, we saw that the capacitance is there in the equation for dynamic power dissipation. To reduce capacitance, you reduce the gate sizes. Right? When you reduce the gate size, it has another side benefit, which is things have become smaller, so you can keep them perhaps closer. So wire capacitance can also come down. So that helps to. So the gate sizing is another very powerful, shall we say, tool to try to reduce power. But with sizing, as you might recall, size affects the speed because size affects the drive current, and so there is a trade-off with sizing, with power and performance. So typically, what is done is that when you have a digital circuit, you have number of paths, right? In any pipe stage between the input flop to the output flop, you have number of paths, and for a synchronous design, the speed of the circuit is determined by the worst case, the longest path, which is called the critical path. Right? So any other paths which are not critical paths, that means their delays are smaller than the delay of the critical path, you can actually slow them down. There is no need for them to be running that fast. You can slow them down by maybe sizing it smaller, and there will be some other techniques, maybe using higher threshold gates and so on. So you are kind of slowing them down so that you are saving some power, but not affecting the overall performance. Another component in that equation is supply voltage, right? So supply voltage turns out to be a very kind of powerful knob to reduce power, right? It has a very effective knob, and one way in which this is dealt with is kind of multiple voltage domains. So when you have a chip with multiple components, you might actually have each of them running at different supply voltages, and so this is kind of like a static setting. You kind of a priori, as during design time, you say, okay, this is going to be in this voltage, etc., and then they run that way. Of course, when you have things running at different voltages, you have to pay attention to the interfaces, right, and make sure that you might actually have to put some additional circuitry so that the voltage levels can be properly understood by the respective blocks, right, and we'll kind of look at that later in the course. But you can also adjust the supply voltage dynamically. It doesn't have to be fixed. It can keep changing during the course of operation. If I find that I'm running things slower, I can reduce the supply voltage so that because anyway I don't need that much speed, so I can reduce the voltage and save. Besides, power of course goes down with reducing speed, but I can save energy also by reducing the voltage. Right? The CV square helps to reduce the energy. So dynamic voltage scaling is a technique now which is also widely used. We'll again look at that in more detail in a subsequent lecture. Remember the equation for subthreshold current, which is a function of supply voltage and threshold voltage. So by choosing different threshold voltages, if I use a low threshold voltage, then I have more leakage. I have faster transistors because drive current is proportional to V minus Vt, the overdrive. Supply voltage minus the threshold voltage. If I reduce threshold voltage, I have more drive current. Things are faster but also more leaky. So here, for example, you have three different threshold voltages for transistors: low threshold, medium threshold, high threshold, and the leakages can vary dramatically between the high and low, and you can have quite a bit of change in the delay also. So you see this is clearly a trade-off between delay and leakage power, and so as a designer you have to kind of decide where you want to be. So clearly in paths which are not critical you can use high threshold transistors because you can afford to slow them down, but you can kind of then recover some amount of power there. But after that, if you want to still further reduce power, leakage power, then you have to trade off between delay and power. Right? You have to slow it down a little bit so that you reduce the overall leakage power. We'll also see a little later that dynamic power and leakage power, right? Typically, they are comparable. The leakage power would be about maybe half the dynamic power. So there is the total power. I mean, there is a good contribution from both dynamic and leakage power. Finally, if you look at these three techniques which we have looked at, what are its impacts, right? If you look at the clock gating technique, basically this kind of like a qualitative kind of rating, medium, again it depends on how much power dissipation is due to the clock and what fraction of the clock network can you get. It really depends on the kind of chip you have, the kind of computations you're doing and so on. So basically the authors say here that it's about medium. There's no timing penalty pretty much with this clock gating, very little area penalty, and you don't have to change anything in your chip. It kind of comes, you don't have to even think about this. Nowadays it's kind of pretty much in the back end, right? When you're writing your design in RTL, Verilog or VHDL, you don't even think about clock gating. The tool basically takes care of it and puts it in, and it's a very simple technique now which is widely used. Multi-VT is another technique where what you do is you can have standard cells with multiple different threshold voltages, high threshold and low leakage, and high speed and high leakage, and the design tool again basically takes care of which one to use when. Right, and again this is very transparent to the designer. You just say, okay, I need to meet this speed, and then the tool will have to figure out what is the right one and so on and use that. You could also have standard cell gates where you have a mix of threshold voltages in the same gate. Some transistors are low threshold, some are high threshold and so on. So those are more complicated gates, but you can make those also. I mean, again, it doesn't have much of a, once the gate is made, it's kind of very easily usable by the design tools for synthesis. Multi-voltage technique can give you, voltage is the most powerful knob, right? Most effective knob to reduce power. So it can give you a lot of benefit, but there could be, because at the interfaces between voltage domains, you will have to have additional circuitry, and the problem is that you could, the overall impact on your design could be high. Actually, because you have to actually have additional pins. You have to think about how to supply those voltages, right? Do you have additional pins where those voltages come in? At the end of the day, at the system level, you have to generate those voltages, right? And you have to get them. So these are the various kind of techniques. Now all these are fairly common now, and these are